students, now we are taking the third part of this light and matter numerical exercise, and let's first of all quickly go through important relations. They definitely will help us in solving the numericals. So our first topic is the Fraunhofer diffraction at a single slit. The arrangement of this experiment is you take a source which is a monochromatic source of wavelength lambda kept at a distance which is equal to the focal length of this converging lens L, so that we get the parallel rays, or in terms of the wavefront we can say that we get the plane wavefront. Now this plane wavefront is coming on a slit which has a width as small a. Now from here the secondary wavelet go in all directions. Since they are originating from a plane wavefront, in order to converge them to give a pattern, we have to use a lens L dash which is kept at a distance, again the focal length of this lens L dash, a screen which actually records the pattern. So let's talk about the secondary wavelets proceeding at an angle theta with the central line. Now in this case, the path difference between the first and the last secondary wavelet is a sine of theta. This you can obtain by simply dropping a normal. So this is going to be the path difference between the first and the last one. So this is a sine of theta. We can always express it in terms of the phase difference, which we normally take as twice of alpha. Obviously, to convert it, as we have discussed in the second part, that you can multiply it with 2 pi by lambda to get the phase difference. Now, the intensity at the point P is A0 square sine square alpha over alpha square, keeping the proportionality constant as 1. This we already have discussed, and obviously we are going to use it. But A0 is going to be the collective amplitude of all the secondary wavelets which are originating from the wavefront of width A. So this is the collective amplitude. So this is factor which is going to decide whether we are going to get at point P, that is a point of interest, a maxima or minima. Now let's talk about the condition for maxima. The condition for maxima are a sine theta must be either 0 or 3 lambda by 2, 5 lambda by 2, and so on and so on. In fact, this is not perfectly 3 by 2. There is a small correction which is to be done. The corrected value is, you can say this is the approximate value. The corrected value is 0 and is 1.43 of lambda, and this is 2.459 of lambda, and so on. However, this is very close to 2.5, so we can make use for all numerical purposes with small error 5 by 2, and for this instead of 1.5 it is 1.43 in fact. So you can use 1.5, it is easy to remember. So these are the condition for the maxima. And similarly we have the condition for minima. Conditions for minima. That is a sine of theta equals to lambda, twice of lambda, thrice of lambda, and so on. And these can be plus as well as negative on the other side if you see. So these are conditional minima. And if you look at the intensity versus sine theta graph, you will get this type of a pattern. So this is A0 square, and you get the other maximas also with continuously decreasing intensity, and this is defined on both sides by the first minima which occurs at a sin theta equals to lambda, or you can say sin theta is equals to lambda by a and minus lambda by a. In this case, sometimes they ask for the width of the central maxima. Width of central maxima. The width of the central maxima is basically 2 theta. If theta is very small, normally it is very small because screen is kept at a large distance. In that situation, you can treat this to be equal to twice lambda by a. That is the lambda by a on this side and lambda by a on this side. So this sometimes is called the angular width, or we can say it's the angular width. Angular width of the central maxima. Now let's take the second point, and this is the front of a diffraction at a double slit. We have 2 slits, and these 2 slits, they are identical. Identical means that the spacing from where the light can pass, that is A for both of them, and the blockage is of the width which is equals to B. It may be same, may not be same. So this is A and A, that makes the 2 slits. And once again we have the similar geometry. We have a source of monochromatic light, a lens which makes the rays parallel, or you can say plane wavefront, and this plane wavefront falls on these 2 slits. Now the secondary wavelets, they come from both of them, and then through this lens they get focused on the screen. Now here it's very important to understand that when we talk about the secondary wavelet going at an angle theta with the central line, then the path difference between the first and the last of the secondary wavelet from the opening, that has a path difference as a sine of theta, which we normally change in terms of the phase difference, saying the phase difference is 2 alpha and is equals to 2 pi by lambda a sine of theta. But there is a very interesting thing, that when we talk about the contribution of the secondary or the second slit, it is almost identical as that of the first one. But diffraction pattern of this and diffraction pattern of this, they get superimposed when they meet on the screen, and leading to the path difference between, say for example, the first one of the first slit and the first one of the second slit. If you just make out, the difference comes out to be, this path difference is equals to a plus b sine of theta. I am repeating it again. We have a diffraction pattern from one slit, we have a diffraction pattern from the another slit, and now that these 2 diffraction patterns, they get superimposed, and in that case we have to compare the path difference, say between the top one of the wavefront or secondary wavelet of the upper slit and the lower slit, and that path difference is equals to AB sine of theta, which we normally change to the phase difference, normally presented as 2 beta, which is equals to 2 pi by lambda a plus b sine of theta. So we have to remember these 2 relations, they are important. If we solve it for the intensity of the light, we get the intensity as 4a0 square sine square alpha divided by alpha square and cos square beta. Look, this is going to be the diffraction term, and this is going to be, you can include the 4 that side also, it depends. This is basically is an interference term. So the intensity contribution can be split into 2 parts just for the sake of convenience, and we get the intensity pattern something like this. So the diffraction pattern will make an envelope in a similar way as we have seen in the single slit arrangement. So this is the contribution of the diffraction term, and superimposed by the another term, this is say beta, that is cos square beta term, which is basically the interference term. As a result, we get the intensity variation going this way. Similarly on this side also. And similarly it occurs here also, and so on. This way, in the same way. So this is a complex arrangement. So let me put sine of theta here. So this first diffraction minima occurs at lambda by 2, as we have seen in the single slit. But in between we also have the secondary maximas contributed by the diffraction term. This is because of this cos square beta factor. So we have this type of the interference pattern in the double slit arrangement. So let's take the third point, that is the front of a diffraction at a diffraction grating. Now this is the most important point in this chapter. So please remember the formulas clearly, and their understanding also is required while solving the numericals. So grating, as you know, is a multi-slit arrangement where once again we take the opening width as small a and the blockage portion of width b. So this a plus b is normally known as the grating element. Rest of the arrangement is similar. You have a source, monochromatic source of wavelength lambda. Lens is kept at a distance equals to the focal length. So we get the plane wavefront. Then this is a grating which is kept perpendicular to it. And another lens which is again is having a focal length equal to the distance between the lens and the screen, so that we get the pattern. So this is known as the grating element. Now sometime when they give grating to you, they give the number of lines per unit length of it. Say for example, it is given that you have a grating with 15,000 lines per inch. In that situation, your grating element will become a plus b equals to 2.54 centimeter. That means this is the length of 1 inch in centimeter divided by 15,000 lines. So this is a plus b. You can change it to meter or any other unit which is convenient to you. So remember, the number of lines in a particular unit, you take a length and divide by the number of lines. So this gives you the grating element. This is one of the very important parameter. Now, the intensity of the light at point P, which obviously is for the case when the angle is theta, is given by A0 sine square alpha divided by alpha square. Once again, this is going to be the diffraction term. In multiplication, we have an interference term. This time it is sine square n beta, sine square beta. Beta, you remember, beta was taken by a plus b. Sine of theta equals to twice of beta in terms of the phase. Right? That same beta as we have seen in the double slit. So from this is a diffraction term and this is the interference term. So we have principal maxima at a condition when a plus b sine theta is equals to plus minus n lambda. Here this n is called order of diffraction. Order of diffraction. It can be 1, it can be 2, and so on and so on. Now we have the condition for minima, and condition for minima is n a plus b sine of theta equals to plus minus m lambda. Please remember, here this number n is the number of grating elements which are covered by the incoming light, right? It may not be the entire number of lines on the grating, it will be only that number which is being illuminated by the light. So this n, and m also is an integer, but this n does not include these integers 0, capital N, 2n and so on, because at 0 we have central maxima. So we also have the secondary maximas in between. If you look at this variation of the intensity, these maximas, the smaller height maximas, we call them as the secondary maximas. So the condition for them to occur is n tan beta equals to 10 n beta. We can find out the position, but this is the main relation to find out the position for the secondary maximas. We also have one of the very important property related to grating, and that is called its resolving power. Capability to see or to separate out the two distinct waves coming to the grating. So this is given by the relation lambda d lambda, and that is equal to number of lines exposed multiplied by the order of diffraction. So if we are looking for the second order, so you have a better resolving power as compared to the first order. We also have the dispersive power. So if there is a variation of the wavelength, these wavelengths are spread out, and this angular spread per unit increment in the wavelength, this ratio is called dispersive power and is given by this relation. Resolving power therefore is equals to the dispersive power multiplied by capital N A plus B cos of theta. Then this collective term is sometimes called the total effective aperture of the grating. And in the last, we have one important point, that is a maximum order of diffraction, or rather you can say it's a maximum principal maximas which we can have. So this number is equals to lambda divided by A plus B, actually is obtained from this relation, that is for the condition for the principal maximas. So as you know, we have the maximum possible value of sin theta is 1. So if you put that as 1 and find out this number, you will get this is a maximum order which is available to you to view on the screen. So let's take the fourth point, and fourth point is the Fresnel treatment for the wavefront. As we know that wavefront is a surface where we receive the disturbance from the source of light in the same phase, or you can say it is a locus of points which have the disturbances from a source of light having the same phase. Now if we are interested to know what will be its role at the point P, ideally we have to take the effect of each and every secondary wavelet produced by this wavefront. But this becomes very difficult mathematically also to find out the effect at the point P. Fresnel suggested that you divide this wavefront in such a way that if I take this central portion and say the nearest point from the central portion to the point P is B, then the maximum distance of this portion from the point P is B plus lambda by 2. That means there is an increment of the path by a factor of lambda by 2. We call this region as half period zone. Half period zone. The next one will be taken as another annular ring like this, but this time the distance from this farthest point to the point of concern is B plus lambda. So you can notice that there is an increment of the path by lambda by 2. So this one is another wavefront region we call the next half period zone. This way we can divide our wavefront into half period zones, and then we try to take their contributions. The point related to half period zone is the area of each zone is pi b lambda. It is same. So contribution starting from the each half period zone is same. However, when they reach at the point P, they are not reaching at the same angle. So as we are going to the higher number of the half period zone, the distance is increasing, even the angle is changing. So because of this factor, we call it as an obliquity factor. Obliquity factor. The contribution of these half period zones, which can be taken as M1, M2, M3, so and so on, they are related as M1 is slightly higher than that of M2, M2 is higher than that of M3, and so on. The third important point is, when we take the total contribution, we have to care for the phase also. You know that first half period zone and second half period zone, they have the path difference that is equals to lambda by 2. And this lambda by 2 path difference is equivalent to the pi phase. And when I say pi phase, it means that if we have crust by one, we are going to get the trough by the other. So if I have to write the total contribution including the phase, I can write this as the M total is going to be M1 minus M2 plus M3 minus M4 and so on. If we have large wavefront and the distance is large, then we find the M total as a special case comes out to be nearly equals to M1 by 2, which actually is defining the rectilinear propagation of light. Now let's take the fifth point, and that is the zone plate. Zone plate is a diffraction device. It is basically a transparent sheet on which we mark the boundaries of the half period zone, say the first half period zone, second, third, and so on. And then we selectively darken the region and keep the other region transparent. For example, if I keep the odd half period zones transparent and even half period zone, that means second, fourth, sixth, eighth, blackened, then we call such type of the zone plate as the positive zone plate. If we do just the reverse of it, that means we keep even number transparent and odd are blackened, then we call it as a negative zone plate. When zone plate is kept in front of a object, say S, maybe a point source, let this distance is A, we find that the light is focused at a particular point P, just like a lens. And the relation we have is this: 1 by A, that is the distance from the object, B is the distance where the image is formed, and N is the number of the zones which are exposed in the zone plate, and Rn is the radius of the nth zone. So this formula is similar to the formula we have, that is the lens formula, 1 by V minus 1 by U is equals to 1 by F. So this is similar formula. Obviously B is on this side, that is going to be positive, but A is on that side, that is going to be negative. So it matches with it. So we have this focal length is equals to Rn square divided by N lambda. Notice one thing, that this focal length of the zone plate has number of such positions. See, the first focus comes at a distance Rn square by lambda. The second focus comes at Rn square by 2 lambda, and so on. So if you have the first focus at this point, you expect the second focus to be at some other point. So this is basically is a multi-focus device, but one thing is clear, that we are not permitting the light to pass through a medium. So this is not suffering with any kind of the variation of refractive index with the wavelength. That means we are not going to get any of the chromatic aberration in this. So this is the advantage of using zone plate. Now let's take the sixth point, and that is the Fresnel diffraction. It is different from the Fraunhofer diffraction because In this case, we are using either the cylindrical wavefront or the spherical wavefront. In front of a diffraction, we were using the plane wavefront, and there we require a lens, converging lens, to make the pattern to focus on the screen. But in this case, what we'll do, we'll keep the screen at the position where we'll get the sharp focus automatically. Right? This is a difference between the two. So let's first of all take the Fresnel diffraction by the straight edge. This is a blockage in the path of the light. This is the line source which is producing the cylindrical wavefront. If I look at the central point O, the half the portion of the wavefront which is in the geometrical shadow region, that is blocked, and only the upper part is going to contribute at O. But if I move from O to the point P by distance y, then even in the lower part of this wavefront, some of the half period zones, they come and they contribute. As a result, we get the intensity in the geometrical shadow region continuously decreasing, whereas in the region other than the shadow region, we have maximas and minimas. The maximas occur at the position given by this formula, and minima occurs when it is given by this formula. This is basically the odd multiple of lambda, and including 2 and n, that is an even multiple of lambda. When Fresnel diffraction is done with thin wire, you can treat as if we have two regions other than the shadow region combining together. Say this particular region is a region which is other than the shadow region, and we have thin wire here. So it means half of the wire is creating a shadow region for one part and remaining half for the other part. So as we have seen in the straight edge case, we have the intensity variation like this. But when it is a thin wire, these edges will behave as if the two coherent sources, and leads to the formation of the interference fringes, and the fringe width in this case is given as lambda d by small d. This small d is nothing but is the diameter of this wire. But if the wire is thick, then this shadow region becomes so vast that we are not able to get the interference fringes. Then we have a continuous decrease of the intensity from both the sides, and these fringes are lost in this particular case, that is for the thick wire. So let's take the first numerical. In this numerical, it's been given to us that the wavelength used in this Fraunhofer diffraction of single slit, it is 5893 angstrom, and screen is at a distance of 2 meter, which is nothing but the focal length of the lens. I'm just making a simple diagram. I'm not showing the lens here deliberately, just to keep the thing simple. And first minima is obtained at distance from the center, that is 5 millimeter. We know that the condition for minima is a sine theta equals to lambda. That is the first minima. This sine theta can be calculated by taking this arc, which is 5 millimeter, and this is 2 meter. So we can closely take it like this. It is 5 into 10 to the power minus 3 divided by 2. Although we are not taking the hypotenuse, because this angle is normally very small, you can see it from this value also. This is nearly 2.5 into 10 to the power minus 3. It is so small that we can treat the sine theta close to 10 theta. And once we know this, we can find out A is equals to lambda divided by sine of theta. So this is 5.893 10 to the power minus 7 divided by sine theta, and that is 2.5 10 to the power minus 3. If you solve it, you will get the value as A equals to 2.5 3610 to the power minus 4 of meter. So let's take the second numerical, and in this numerical a monochromatic light is allowed to fall on a double slit. The wavelength is 500 nanometer. The screen is kept at a distance of 1.5 meter. The slit width is given as 0.02 and each of them is same. And the separation between the two slits is 0.1 mm. And we are asked to find out the angular separation between the first and the secondary minima. Right? Remember that. So for secondary minima, the first one, the condition is sine of theta 1 equals to lambda by 2. So sine of theta 1 can be taken as lambda by 2 a plus b. Obviously this is 5 into 10 to the power minus 7, 2 multiplied by 0.02 plus 0.1. Since it is in millimeter, so I have to write 10 to the power minus 3. And if you solve for the theta 1, the value comes out to be 0.1194 degree. Similar formula is to be used to calculate the angular position of second minima. Now this is the secondary minima. So the condition is a plus b sine of theta 2 equals to 3 lambda by 2. So sine theta 2 therefore is 3 by 2 lambda divided by a plus b and is equals to 3 by 2, 5 into 10 to the power minus 7, and when you add it, this is 0.12 into 10 to the power minus 3. All units are taken in SI system, so there is no need to have a correction for it. So if you calculate for theta 2, you will get the value as 0.3581 degree. So from here, if you calculate the separation, the angular separation will be 0.238 degree. So this is the answer for the question number 2. Although the distance given to the screen can also be used, although it is not required in this particular question, but if they ask you to find out the linear separation, if is there, this is additional one. If it is linear separation is required, so linear separation is going to be capital D multiplied by delta theta, because angle is very, very small, so you can straight away take it. But remember, when you use this delta theta here, you have to convert it into radian, right? This is important, because whenever the angle comes alone, it should be taken always in radian if you are working in SI system. So let's take the third numerical. In this numerical, it is given that the two wavelength 5890 angstrom, 5896 angstrom, these are the two lines in the sodium light, is subject to a grating which has 15,000 lines in an inch. The focal length of the objective lens of the telescope is 25 centimeter and of the eyepiece is 1.8 centimeter, and they are asking for what is the angular separation for the first order diffraction by the grating. Now we know that the principal maxima from the grating comes in the condition when a plus b sine theta equals to L lambda, where A plus B is called the gridding element. So let's first of all calculate the gridding element, which is equals to 2.54 centimeter. That means if you convert it into meter, it is this much. Divide by 15,000 lines, and if you calculate it out, this comes out to be 1.69 10 to the power minus 6 of meter. Since we are talking about the first order, so obviously the n goes 1, and we have this formula A plus B sine of theta equals to lambda. This condition clearly shows that if there is a change in the lambda, obviously there is change in the theta. But this angle is just immediately after the grating. But when it enters into the telescope, it gets modified because of the focal length of the objective lens and the eyepiece, which we have to care. So let's first of all find out the angular separation immediately after the grating. So first of all, let's calculate it for 5893, or do one thing. Take this A plus B sine of theta equals to lambda and differentiate it. So this comes out to be A plus B cos of theta d theta equals to d lambda. So we can calculate this cos theta, since cos theta is equals to A plus B under root of 1 minus sine square theta, this is d theta, d lambda. So obviously the d theta which we are looking for is equals to d lambda divided by A plus B under root of 1 minus sine square theta. From here I can write the sine theta, which is equals to lambda divided by A plus B whole square. So from this relation I am able to get the d theta in terms of d lambda. But here we have to use the lambda. Which lambda is to be used? So when you have these two wavelengths very close to each other, the lambda will be taken as 5893 angstrom, which is the average value of the two. Rest is mathematics. You just simply put the difference in the wavelength, which is 6 angstrom. 6 angstrom means 6 into 10 to the power minus 10 in angstrom. This is the value. A plus B, already we have calculated. A plus B is 1.69 into 10 to the power minus 6 under root of 1 minus wavelength is 5.893 into 10 to the power minus 7 divided by the value A plus B, which is 1.69 into 10 to the power minus 6, and take the whole square of it. Now if you calculate this d theta, this comes out to be 3.79 into 10 to the power minus 4 radian. But this, as I told you, is just immediately after the grating, right? They get separated. But when it get modified by the telescope, we have to do like this. So let's say telescope says that the angular separation is d theta 1. So this is going to be the d theta multiplied by the focal length of the objective to the focal length of eyepiece. This formula we are able to get from the magnifying power of the telescope. Magnifying power, that is the image angular width divided by the object angular width, is equals to the focal length of the objective to the focal length of eyepiece. But this is for the normal adjustment, right? This we have to keep it in mind. So d theta 1 is going to be 3.79 10 to the power minus 4 multiplied by focal length of the objective, which is 25 centimeter, divided by 1.8. And if you calculate this out, this comes out to be 5.27 10 to the power minus 3 radian. This is the angular separation which is required in this numerical. It is straightforward numerical, but the only thing is that the separation we have to calculate as seen by the telescope. So let's take the fourth numerical. In this numerical, it is given that there is a diffraction grating where the slit width is 1.5 micrometer and slit width plus spacing in total is 4.5 micrometer. And they demand that find the lowest order that will be absent from the diffraction grating. Let's first of all understand why a particular order is missing. We know that when we get the intensity information from the diffraction grating, there are two parts in it which are multiplied together. One is called the diffraction component and other is called the interference component. Or you can take it like this, that each slit in a grating is doing its diffraction and all these diffraction patterns, they interfere to give you the resultant intensity. Now condition for the principal maxima of the grating is A plus B sine theta is equals to N lambda, where N is the order of diffraction. But at the same time, A sine theta equals to M lambda is the condition for minima of single slit diffraction. Now look at the situation. If each slit is having diffraction and this minima condition is matched, whatsoever the case may be, when they interfere, obviously they are going to give you the minimum, that is zero intensity. So it means that if these two conditions are simultaneously satisfied, then we are going to get the minimum. In order to find it out, let's divide them. This comes out to be a N M, where N is an integer, remember it. So when we put this value here, 4.5 micrometer divided by 1.5 micrometer N by M, this comes out to be 3. That means N is equals to 3N, where M is an integer and the minimum possible value of this integer is 1. So obviously the missing order are going to be 1 multiplied by 3, 3, 6, 9 and so on. So obviously the minimum number of this order which is missing, that is 3. So N equals to 3 is your answer. Now let's take the fifth question, and fifth question is on the resolving power of the grating. This grating has 15,000 lines per inch and light from the sodium source is taken, which is having a wavelength of 589 nanometer, 589.6 nanometer, and the length which has been exposed is 0.075 centimeter. We know that the resolving power of the grating is given as capital N into small n. This is order of diffraction, and this is the number of lines which are exposed. So to find out this number n, we'll have lambda d lambda divided by the number of lines which are exposed. The wavelength is to be taken as the average of the two, and that is equals to 589.3 nanometer minus 9 divided by the difference of the wavelength is 0.6 nanometer. And to calculate the number of lines exposed, since it's given to us that the length is 0.075 centimeter, So it is given that 2.54 centimeter contains 15,000 lines. So 15,000 lines per 2.54 centimeter multiplied by the length which has been exposed, that is 0.075 centimeter. This will give you the order. If you calculate this, you will find the value comes out to be 2.21. Obviously, the decimal orders are not allowed, it's only the integral value which is allowed. So the number which is minimum possible is 2. That means you can get these result only in the second order of diffraction from the grating. So let's take the sixth numerical. In this numerical, a circular aperture of 2 mm is given, exposed to the radiation of 500 nanometer. In a very first step, he is asking us to find out the radius of the first half period zone. We know that the radius of the nth zone is equals to n lambda b. We have discussed this point in the beginning. So since we are looking for n equals to 1, so radius is going to be under root of the wavelength, which is 5 into 10 to the power minus 7 multiplied by the distance, which is 2. So obviously this comes out to be 10 to the power minus 3 of meter, or you can say it's 1 mm. This is the first part. In the second part, he says that how many such half period zone can be accommodated in it. To find out, let's take this radius this time to be the radius of the circular aperture, that is 2 mm, and this is the number which is possible, maximum, lambda, multiplied by the distance b, which is 2. Wavelength given is 5 into 10 to the power minus 7 multiplied by 2 under root of n, and this comes out to be 10 to the power minus 3. This is 2 millimeter which has been given to us, so we have to multiply it by 10 to the power minus 3. So 2 into 10 to the power minus 3, so this is out. So n comes out to be 4. It means we can get 4 half period zone fitting to this circular aperture. Now to calculate the contribution, that is in the third part, we know that the total contribution is m1 minus m2 plus m3 minus m4. Now as we have discussed during the rectilinear propagation part, this can be written at least as m1 by 2 minus m2 plus m3 by 2 plus m3 by 2 minus m4. So this part we can eliminate because there is a linear decrease. We expect this is a small decrease. So the resultant contribution is going to be m1 by 2 plus m3 by 2 minus m4. This is the net contribution of the half period zone at the point of . So now let's take the seventh question. In the seventh question is given to us that the radiation has a wavelength 600 nanometer. So for this zone plate, the radius of the first half period zone is 0.3 mm. So we have to find out its focal length. Also we have to find out the radius of the third half period zone. Now we know that the radius of the half period zone in terms of the focal length is given as f, or you may write the f as Rn square divided by L lambda. So it's given to us that the radius for the first is equals to 0.3 10 to the power minus 3 whole square. Since it is the first half period zone and the wavelength is equals to 6 into 10 to the power minus 7 nanometer, this is 600 nanometer. So the focal length comes out to be 0.15 meter. Now the next we have to find out the radius of the third half period zone. Now third half period zone is obviously is equals to 3 lambda into f. F already we have worked out. So this is going to be 3 into 6 into 10 to the power minus 7 multiplied by the focal length. Focal length is equals to 0.15 meter, and this is 5.2 into 10 to the power minus 4 of meter. This is R3. So these two are the answers for this question number 7. Let's take the 8th question. It is given that the wavelength is 6 into 10 to the power minus 7 meter and screen is placed at a distance of 2 meter, and we are asked to find out in this Fresnel diffraction from this line at a distance of 1 millimeter what is the intensity. Let me remind you, we have seen that in a straight edge case, the intensity increases from this position, that is a position just immediately at this, in front of this end of this edge, and there is an increment in the intensity, and this is the distance. Let me say this is y. So let's calculate. To calculate this, first of all we have to calculate the Fresnel parameter, which is equals to y under root of twice lambda b. This is given to us is 1 millimeter, 1 into 10 to the power minus 3 under root of 2. The wavelength is 6 into 10 to the power minus 7, and this distance b is 2 meter. If we calculate this, we get the value 1.29, which can be taken like this, that when we are at this particular point, from this wavefront, the central portion of the wavefront, right at this particular point, if I join this origin, in this portion we are getting few half period zones, they are contributing, although this whole upper part is also contributing. So the net resultant contribution is contribution from the upper part, that is m1 by 2, but from this lower part the contribution is only 1.29 of the half period zone, which can be written as m1 minus of 0.29 of m2. To reasonable approximation, we can treat m2 to be close to m1 because there is a decrease, but decrease is quite small. So this comes out to be m1 by 2 plus m1 minus of 0.29 m1. Although I am doing a bit of approximation in this case, just to keep it simple. So this comes out to be 0.5 plus, and this makes it 0.71 of m1, which is 1.21 m1. So as far as the intensity is concerned, so at this point P, the intensity will be 1.21 whole square m1 square. Remember, at this point O, the contribution at O is only m1 by 2. That makes the intensity at O m1 square by 4. So if we compare it, IP to I0, this comes out to be 1.21 whole square divided by 4. And this value comes out to be, if you calculate, this is equals to 1 by 4. This is 1 by 4. This is 1 by 4, m1 square will be out from the scene. So this is 4 multiplied by 1.21 whole square, and this is 5.856 of intensity at O. So we can say at this point of interest, the intensity will be 5.8 or 5.9, you may say, 5.9 times nearly more than the intensity at the point